This is actually a re-recording of Prof. Zoe's QC simulator. I want to make this a little slower and clearer than what we did in the original webinar. We're going to go through the objectives of the webinar, this time with real numbers and with visuals. Tab 1 on current risk answers the questions, how good is good enough? And is the method good enough now? The second section deals with, would you know if it wasn't good enough? How to design the QC, and you're going to design QC processes from a simple table based on margin for error. Finally, we come to potential risk, where you bring it all together. You can compare the cost to control quality with the potential cost of failure to control quality. And the final tab is simply some calculators I've thrown in so you can check the math on a few things you may be doing. Once we go into the simulators, they follow this same principle. A number is a thing of awe. Numbers come from opinion or fact. So if a number is selected from one of several possible choices, that's based on opinion. The lab director defines the source of the medical goal, the true value, and the acceptable risk limit based on medical opinion. You cannot calculate medical opinion. You cannot calculate acceptable risk or medical goals within your lab. That would be like trying to calculate the speed limit based on the speed you've been driving. There are only 4 numbers that the lab controls. Your opinion drives these numbers, nothing else. So let's go into the simulator. Tab 1 deals with current risk. I've divided it into sections just so we can take this trip rather slowly. We start with dealing with the risk drivers. These numbers drive current risk. We're going to give you, as we go through, more numerical information and more visual presentations to see exactly what's going on. And based on the numbers you put in, without seeing any of this, the computer can decide if risk is acceptable, yes or no. It makes that decision based on these risk drivers. The peer mean is the best source of the true value. I used to teach, here's 5 ways to select the true value. The peer mean is the best source of the true value. We used for the 10 years we practiced this in the Cochrane Region program, we would set the peer mean on month 1 or month 2 of a new lot number, and it would normally stay consistent throughout the lifetime of a 2-year control. Current mean, however, changes with every reagent lot change, as instruments change, as people change, the current mean changes with every calibration a little bit. The current SD changes. These are based on facts that come from the instrument. The medical goal and the acceptable risk level are based on the opinion of the medical director. Every time you change one of those 5 drivers, the assessment of whether risk is acceptable or not can change. We're going to start with a current mean value of 100. And at that point, the risk is acceptable. The medical goal is plus or minus 10. So obviously, if my current mean is 90, that's not acceptable. If the current mean is 105, however, that mean is acceptable. But if the current mean is 105 and the SD is 3, then it's not acceptable. That is all based on simple logical mathematics. Now let's take a look at the actual numbers and how the computer makes the determination if risk is acceptable, yes or no. It's a simple calculation. Remember, risk estimation is the process used to assign values to the probability of occurrence of harm and the severity of that harm. You can mathematically calculate the probability of occurrence of a medically unreliable result, a result that fails the medical goals. Risk bars and risk charts simply show you that calculation, show you what's going on. They show you where you are versus where you want to be. These are the risk bars. These are the charts. Every time you change the mean or the SD, the visual information that you receive here will be different. Okay, let's take this live. This is Prof. Zoe's QC simulator. We're on the tab for current risk. We have the same risk drivers you've seen in the PowerPoint presentation. These are the risk bars, the risk evaluation chart, and the calculations. We're starting where we were there with a current mean of 96 and a current SD of 1. Watch the visuals and the numbers. When I change the current mean to 100, now you can see that on both the risk bars and the risk chart, it's centered around the true value, which is the peer mean. If the peer mean was 98 instead, then this would be a positive bias. If the peer mean was actually 95, this would be a stronger positive bias. But if the peer mean was 106, then we have a negative bias. It's the relationship between the peer mean and the current mean that determines accuracy and bias. I'm putting this back to 100. I'm going to move the current mean up now to 104. This, folks, so now the current mean is 104. You can see it has a positive bias. Just looking at the risk bars and the charts, you can see it's quite a good distance from the red lines that are the failure lines. When you come to the numbers, the current risk is 0%. The margin for error is 4 SDs. That means it can shift 4 standard deviations before risk becomes unacceptable, and a sigma value calculated from the same numbers would be 6.0. So this is a 6 sigma method. So let's see what that means. It says the margin for error is 4. It can shift 4 SDs. Let's try it out. 105. And that looks fine. The risk is still 0%. The margin for error dropped to 3. The sigma dropped to 5. If I go up to 106 with a new calibration, the risk is still acceptable. You can see visually that it's getting closer. And now it's not quite 0%. This is still a margin for error of 2 or a 4 sigma method. So we've shifted 2 SDs. Let's go up to one more to 107. This method can only shift 1 standard deviation before it will fail. This is a 3 sigma method. The risk is still acceptable even though it's much higher than it was before because it's still within the acceptable risk limit. And if I go up that 4th standard deviation to 108, now the measured risk, 2.275, is equivalent to the acceptable risk that is not acceptable, and you should stop. The math is just that simple. Let's bring this, oh, wait a minute. Okay, I'm going to bring that back to my 104 or 105 again. And you see we have a risk value of 0. My sigma is 5, my margin for error is 3. Bring it up to 106. This is a 4 sigma method on one side of the street. But what if the clinical chemist crosses the street? What if the clinical chemist believes that we should be using biological variation and comes here and says that the desired biological variation allowable limit is 6.96? So I'm going to come back over here and enter 6.96 as my medical goal. The same method that is acceptable on the north side of the street is unacceptable on the south side of the street because when you set your medical goal based on the biological variation limits, this is now a method with a sigma of only 1. The margin for error is -1, and 16% of your results are already failing, if you believe in biological variation. However, if you bring in a new clinical chemist and they believe in CLIA instead, then you're perfectly fine. The question you want to answer is the risk of a patient receiving a medically unreliable result acceptable? Yes or no? The risk of a patient receiving medically unreliable results depends on the physicians who are going to make the decisions about those patients, much more so than on the personal opinion of somebody who's arbitrarily setting medical goals so that one side of the street things fail and the other side of the street things pass. There really must be a medical goal based on medical opinion. We're going to go back to the easy way. We'll set it back to the CLIA limits. But now I'm going to come down here and I'm going to say, I'm going back up to 10. Well, no, let's bring the SD up this time. That looks like more fun. I'm going to increase my standard deviation to 1.5. Now, if I believe that the acceptable risk level should only be 0.1%, this method is unacceptable. Is this a reasonable or unreasonable assumption? Is it a decision that should be made within the medical lab, or is it a decision that should be made by the medical director? Should it be weighed with the consequences, the cost of the results that are being reported? How many results will be reported if you set your acceptable risk level here versus at 2.23? Those are the questions. Now we need to go into more numbers to answer those questions.